Okay. Need this one. We are sharing this screen. Look at that. What are you, hanging out there in Colorado again? What's that say? Piney Lake? You, James.
Well, he was in here in the mechatronics lab about 20 minutes ago, so
Well,
he's definitely not in Colorado.
nah, it's just a sweatshirt he's got on. Um,
Oh, I know.
cool. So we got that. And then I get tablet set up, and we think we can get to business. All right. So cool. And we are live with a bit of a delay because of the different devices. Okay. So I think we're good. At least I hope we are. All right. So what's your nickel, folks? What is it you want to? Where do you want to start? How do you want to start? Laura, you started this, although Matt, you prompted it earlier today. So you're still muted, Laura.
Yep, it took a minute. Um, I was gonna ask, are we going off of the big project that the other kids did that you were showing us, or are we going off our like completely own thing?
Well, you got your completely new sizes from what they had, although we stuck pretty close. But didn't we change the
Mm-hmm.
horsepower and some other things? Which reminds me, where is that? Right here. She dug that up.
I believe we did.
So we went to
Okay.
10 horsepower and we did 500 RPMs, which gave us a torque of about
Okay.
1260. And they had 240 RPMs or something like that. Yeah, they had some weird numbers in there.
Didn't you say you changed it? Didn't you change it to to 3 horsepower or something like that, so we didn't explode the gears? I was talking
Yes, we
to
did. And that's kind of the things that
James,
I
and he said we
was
did
we're talking about that changed. I mean, I'm not saying I got the numbers right here. So that was their project. Oh yeah, here we go. So we assumed 500 RPMs at 10 horsepower, and then that didn't work. So then we went to 240 RPMs, and then we changed. We changed. Could have sworn we changed something there. Yeah, I think it was three. It was like 3 horsepower in order to get the gear to work because of the power on the other gear, but um, which makes a difference because you're going to need to calculate your shaft and that sort of stuff. So does anybody else remember what the horsepower was we finally derived at? James? Can we ping him awake?
I don't remember. I just have the 10 horsepower at 500 that we originally started with.
Yeah, but James is the one looking up all the gears and stuff on Boston Catalog for the last couple of days. So
I was talking with James earlier, and he said that it was 3
was it?
horsepower.
Okay. So let's start with this in our project statement then. He's waiting in the lobby. How can he be waiting in the lobby? He's right here.
I had to switch computers. The computer I was on didn't have audio or video.
So that's why you're not answering the thing about Piney Lake.
So yeah, we had what I had written down was 3 horsepower with 500 RPM. We had explored the 10 horsepower with 240 RPM, if I remember correctly. And I think that was still too high. So we bumped it to 3 8 horsepower at 500.
And that
And
gave
was
us
well
the
within our cylinders.
YF 100 gear, right?
Yep. That gives us a torque of, I have 378. And then that should put us within tolerable limits for our bearings in terms of weight and everything.
So that's our torque. And did you guys calculate the, we got this gear and we got the pinion. And what we're looking for is this one and that one. So we need WT and WR. Did you calculate those yet?
Yeah, I have WT as 37.8 and WR as 13.76.
And that's in pounds.
Yep, pounds.
What's WR?
13.76.
Okay. And WR is the one that leads us to the bearing selection, right?
With the bearings, at least in the report, our design constraint was that the bearings could take no more than 50 pounds at maximum speed. Eccentric loading.
Do they have a speed they're specifying?
They originally specified 240, but then we changed it to that 500 RPM.
So we just presumed it was going to be 500.
Yeah.
Okay.
And that's what the design report was asking for. I'm not sure what our bearings were able to actually tolerate in terms of what we picked, but that was the design constraint that we had from the report.
Well, that's what we're going to play with then. So, all right. So literally we have these things from the, this is all the stuff from the gear design. You know, I want to call it, I'll call it a chapter. I don't even know what chapter it was, but we had to come up with WT and WR. Okay. You don't have to go through all the calculations for all the pitch diameters, but you do need to show where those came from. Okay. Everybody make sense? Matt, you look weird without a baseball cap on.
Yeah.
Sorry.
I'm also in like my childhood bedroom, so
Whatever it takes.
whatever it takes.
If you're talking, well, not as bad as who was that student last year that was in an HVAC class. And he was literally laying under his truck fixing a bearing on the drive shaft and talking to me while he was doing it.
Oh yeah, I've heard that story before.
Anyway, so okay, so we're at these are the specifications. So you do need to, you know, show WT, WR, where they came from. Okay. Everybody good with that? You know how to do that?
I was going to ask what those equations were.
So you go back to the section on gears and you'll find them, but it's
Okay. I'm sure it's in here in the OneNote.
so let's just scoot back here and we'll find them.
I've got them right here. It's TC over RC is your WT equation.
Right.
And that's going to be your torque over your diameter, your gear diameter.
Or if you look at this one, and we got, remember doing this bit here with WT is power over velocity. Okay.
Okay.
So that'd give you the WT. So there's a couple ways to get to it. It's not like it's all just straightforward in one way or the other, but this one actually makes sense because the velocity, you know pi, you know your diameter, you know your RPMs that you're trying to shoot for, and you got the conversion for it. That gives you the velocity. And then put your 3 horsepower in, other than doing the conversion to make sure horsepower and velocity all wind up in the right units. You're pretty good. Make sense? Okay, so that's that one. And then the only other thing I would check with this is this gear got the strength to have, where'd it go? The face width of the tooth here. Does it have the strength to actually maintain the the forces that you're putting on it? You know, because the last thing you want is a gear tooth to break off because there's not enough metal there. And you put enough metal in a gear tooth by making it wider because you can't change the cross section of it any. All you can change is the width. You don't have to put a hat on for me, Matt. Sorry.
My hair's getting my own face.
Does that make sense, Laura? You know what to calculate? Okay.
Yes. This is making a lot more sense
Okay.
now.
So this one's really easy from the power over velocity. WR is going to be the where are we getting that one from? That's the what'd you have for equation there, James?
For which
WR.
one?
It's tangent something.
Yeah, it's the tan of your what's it called? We use 20 degrees. I forget what the angle
It's
is.
20 degrees in this one.
Yeah. That times your WT.
Thank you.
Oh.
Oh, you guys can't see what I just wrote on the screen. Duh. Right here. So it's those two equations. All right.
Okay.
And those are the things
Yeah,
that
that's
really
all.
came out of this. Sounds stupid. We spent 3-4 days on gears, and this is what it results to when you really do a design. I mean, you're not designing the gear. That chapter was about designing gears. This is about selecting gears now. Makes sense? Okay. Now, the interesting thing to that is we have the shaft to design yet, and that comes down to knowing horizontal and vertical loading. Okay. And that's the stuff, which, by the way, Matt, someplace I just did one of your homework problems. That's exam 2. That was okay. No, you did that part okay. What the hell is missing here? Oh, yeah, I know what's missing. When we get the max moments from these guys, so you get a max moment H, and you get a max moment V, you still got to put that into Pythagoras theorem to come out with a reaction that is the resultant of those two. That makes sense? Yeah.
Okay, yeah.
Funny part is, I actually saw in your homework you put the number in, but I have no idea where you calculated it. So either you're really good at making magic happen, or you did do it and didn't write it down. So
Yeah.
okay, so when we get here, we need to go.
So this is basically like we did our this would be like our first after our problem
Oh
statement.
yeah,
This is like our first two steps. Like if I'm looking at the parts that you wrote, this is like all of step 2,
pretty much. Yeah.
right? With the horsepower and the RPMs, and then we just
Yeah. So I mean, it's if you go back
Gears.
to shaft design, not that one. Shaft homework problem, not that one. L20 shaft design. Is this where'd I put the stupid little not there. Shafts. Where'd I put the goofy steps for shafts? Well, I could have been a lot better at organizing these pages. Where did I stick those things? I have no idea. Cool. Let's do this. We're going to find them right now if it kills us.
Are you talking about the design procedure that we
Right.
posted? It's L18 shaft design procedures.
L18. Yeah, right there. So that's the stuff we're really at now, is doing this. So your horsepower and the shaft and all that stuff is initial stuff to get you what these are, because in your shaft you didn't have these values to or the stuff given to you. You had to choose the gear, which you did. Okay, so based on your initial horsepower, you shopped for a gear at Boston Gear Catalog. You said this gear is going to work, and now you're trying to confirm that gear actually does work. And then from there, once you know that gear works, then you're going down to do all the rest of the shaft design. Make sense so far? Got a couple nods.
Yeah.
Yeah, makes sense.
Okay. And then really when you get done, it's just a matter of, well, before we get to that, we did the calculations. No, we did nope. Where did we do that? Stop zooming in like that. Oh, yeah, it was. So in order to get to these 3 designs, we kind of made some guesses on what we'd like it to look like. Okay. And then based on that, I'm going to use a decision matrix to decide which one actually is going to work better to solve the problem. But this could come before the calculations, or it could come after the calculations if you do 3 sets of calculations. Okay. But depending on what you put in this, you may need to choose certain calculations to become part of the decision matrix.
And with this whole project, I know we kind of picked gear to go with and a type of bearing to go with. Would it be okay to choose a different bearing if we decide that the current bearing isn't what we want for our design? Or do you want us to stick to what we've already picked?
If you decide that bearing sucks, you go back and pick another bearing. And the
Perfect.
the big thing here is to remember that the design is an iterative process. So you choose stuff up front, you verify through calculations whether it's going to work or not, and then when you get it to work, you're golden. But the real trick is knowing when to stop, because you can always find something to say, well, if I made that a little better, if I got rid of that step in the shaft, if I put a chamfer here, by the time you get done, you're never going to get a product out, which is usually what your
Yeah.
boss is after you about, is trying to remember to stop your design process someplace and just create the thing. So that's kind of the steps you're looking for there. Buddy, good so far?
Yeah, that makes
Okay.
sense.
I'm just a bit confused as to like, so I get that you need to get these calculations that we just discussed, the WT, WR, and all the stuff for the bearings and the gear, but then like what am I weighing that with, like, in terms of like deciding if that will like work out for putting it on my shaft?
So you need to make up some specifications that okay, so I think I think I see what you're looking for. So you're looking for let me get back to the right screen here.
Like because I get how to do all these calculations, and I'm following more and more as we talk about it, as like where to go from step to step. But I guess like that's like the that's basically it for me. Like I don't know how to interpret these numbers.
Decision matrix. What the hell am I writing? All right, so you got to come up with, you got a bearing that is under 50 pounds loading, right? You got a gear that's got to be 10 inches in diameter, correct? And we want it to be, and this one actually could have two. You could have a 3 horsepower requirement on it, right? We chose that. Okay. We need a shaft, and we got a keyway. We got the ring groove. We got let's see what else. Oh, the step. Call it step size. Okay. And oh yeah, back to the bearing here. We got so that's the key, bearing bearing shoulders. Okay. And all right, so probably a couple more we could find there. Well, yeah, we know we got to have we want a stress that's going to be, we want stress of yield less than the yield strength. That'd be one specification you can easily do. All right, because that's going to be the calculation you're going to put in the, your maximum distortion energy theory thing. That's what you're checking there. You could specify a factor of safety, but I think once you do that, you're going to see that that's all still part of the these two equations here. What else? Did we have any specifications
with
from the original team on shaft size?
no, just the gearbox sizing, which we defined as the maximum height essentially for that we could have for the gear was between 6 inches and 12 inches was our goal for that. But then the max for the shafts, so the max width we set as 3 to 6
Okay.
inches.
So gearbox height, 6 to 12 inches, and then the shaft width was.
That's kind of how I have it drawn out.
Back up just a wee bit, James. Yeah. So the shaft width has to be 3 to 6 inches. All right. So that comes down to. All right. Well, before we do that, let's just save that one for a little moment here. So we got design 1, design 2, and design 3. And you guys can't see that. Okay. So with those guys, we want to rank each of those designs we came up with, and those are the drawings from the other page. So you're going to put those 3 designs in your report and say, these are our 3 initial designs. They meet this decision matrix, put that little table together, and put number values on it. And then whatever one ranks out the highest, that's the one you're going to go with. All right. Now, some of these are going to require some calculations to do it. Okay. So gearbox height, that was pretty much determined by the overall size of the gear. Okay. So do all these meet it? Yeah. Right now we're using a 10-inch gear, so we're under 12. Okay. The only thing I would do maybe to check this was, and it wouldn't be so much the height as it would be the width of the gear box, knowing that the pinion and the spur gear would be in a certain width of the box too, not just the height of the box. Okay. But I bet if you make a 10-inch gear fit in a 12-inch box, well, no, because you could get a 2-inch pinion and you'd be rubbing on the outside of the box. So your gear box in the width or the length of it may be 14 inches. We're not going to get into that kind of specification right now. If you can keep it under the 12-inch, we're good. Make sense? Okay.
With the shaft width, where are we going to find the measurement for the width of the gear and the bearings? I've been looking on Boston catalog and I'm not seeing any widths there.
Cool. I don't know.
Although there's face width. Would that be the width of the
That's
gear?
your
Or would
face
that be
width of the
something
gear.
else?
Yep.
Okay, so that would be 1 1/4. So yeah, that works.
So gear face width.
Just trying to think if we can keep it under 6 inches, you know.
Is 1 1/4 inches. Okay. And that's a number right there too that goes back into the gear section and calculate the face width of the gear tooth and see if it's going to work for you. Okay. Because that's all plays out in the stresses. Okay. So this one, you got to check against gear calculations. Okay, for the stress of the gear. Good there? Okay. Now the other thing is, so we got a shaft like so, and we are going to put a gear in here like so and stick out the other half of the shaft this way. Okay. And we got to get the bearings on the end of this. Okay. And we already got 1.25 inches here. So if we got anything left, we got 4 3/4 left of shaft.
Hey, where are you writing this?
Oh, down the page here.
It's in the bottom of this page.
Oh, oops.
Sorry.
Thanks.
So I'm working on the tablet separate from the computer screen. All right. So, I mean, we got bearings here. What are the widths of the bearings?
Let me go to what we have selected.
As long as you're there, give me the make and model number of them too.
Okay. The one that we picked so far is the 6H1 and an 8
Yeah, that's what I have.
Octo block.
too.
And has bore size, it has overall height, base to bore center line.
Base to bore center line would be this distance. Let me get rid of this one for a minute. It would be this distance here. So there's your base to here.
Can we take the overall height, subtract it from the base to bore center line, and assume that's our radius? So like the total height of the gear, or not the gear, the bearing minus
we-
that
Yeah, you
base.
could. Do we really have a requirement to do that, or is that just extra minutia?
I'm trying to, well, I guess we don't need that. I'm trying to think of how we'd get the width. It doesn't have it written outright.
Must be a standard one there at the beginning because they were probably all the same width. So for that 6H, 1.125 1.125 is the bore diameter.
Yep.
Cool. Let me go up and get a Boston Gear catalog out here. And the e-catalog, where'd you go? And it was a 6H. Yeah. That was a dash. Fine. Do it this way. Eccentric shaft lock for international manufacturer. Well, we know what the H series is now, so hold on, I'm going to put this over here. All 111 pages of it. Pillow blocks on 215 to 222. Whoops, not 2015. Cool. That's page 135. All right, I'll do it the hard way. No, that sucks. Okay, let's see. This thing is, give me a page number. 143. And we're going to go 215. So let's go for 100. Hey, look at that. Stainless steel pillow blocks. So you get a food grade grease. Cool. Not what we quite want, but let's go back this way. But the answer to your question is right here, basically. You need S. The measurement S is the width of the bearing in this pillow block. So once we find our 6H's, we can actually do that. There's a 6A. MP. This is the coolest thing too about the old paper catalogs is you'd get to the point where you use the same bearings over and over again. So you just kind of put a bookmark in that page. That's an FT.
And so we're going to want to do this for collars as well, right? Just so that we can find the collar widths as well.
Why did it just go from flange bearings to mounted ball bearings? Mounted ball bearings. Mounted ball bearings. Now there's a hell of a bearing.
James, what do you mean collars?
What's up?
What did you mean by what you just said?
With the clamps. So essentially we need to make sure that our shaft is shorter than 6 inches. And so that's the maximum amount of length that you have to fill. So if your gear eats up 1.25 inches in the middle, you lose that much. Your bearings are each going to eat up however much on the ends. And then you still need, if you need a collar to lock the gear in place, that's going to eat up some more as well. The ring groove
kind of stuff.
So you need, yeah. And so just taking all that into account to make sure you're not over that 6-inch parameter with your shaft length.
I don't get why they don't give us the, there's the S. All right. Well, so we're going to have to either find the exact SH or choose a different bearing, but S from the left side over to the center line of the bearing is for 1 3/16 inches is 0.874 or basically 7/8 of an inch. So you're literally going to have 14/16 is, that's not right. 14/8. It's 14/8. Inch and 3/4 is going to be consumed up on each end with the bearing. So if I go back here for a second and let's do this, we are 1.75 inches on each end. And we got 1.25. So that's 3.5. Yeah.
Just
And
under
that doesn't
5.
leave us anything left over, really. I mean, we literally get a shaft that looks like this.
Yeah, and that's like the
Yeah.
size.
I mean,
the
is that
scale.
doable? Sure, as long as everything fits in there. And then the question becomes, you know, now it affects you back to your selection criteria. Do I go with shaft 3, which has a step shaft in it? Do I just get away with just 2 ring grooves because I tell you what, there's not a whole lot of room left, and some poor schmuck's got to put this thing together, or how do I deal with it? You know, maybe it comes down to you try to shoot for the 6-inch length and realize this is totally stupid. It's never going to work. But then you're also looking at this thing, and we got a shaft that's 6 inches with a point load on it of whatever the WR, and we got a reaction here and a reaction there. And then we got this bit over here, still 6 inches, reaction L, reaction R, but this is now WT, and we got to do all the shear and bending moment diagrams to come up with our max moment in the radial and max moment in the vertical. How many M's can I put in that one statement? Or in the tangential, actually, this would be horizontal. Let's do that because that's what I've been calling it before, and this one is our vertical. Make sense? And then we're going to go back and find our max resultant, and that's going to be the square root of M max V squared plus M max H squared, and we get that, and that becomes stress is equal to MC over I, and we figure out whether the stress is what the stresses are. Go calculate your maximum deflection energy theory and see whether or not you stay safe. With me? And literally this project is everything we've done this semester. But it's not in the straight up direction we did it, because when we were doing it, we were taking all those pieces apart and focusing just on that one section. Now, in order to do this, you got to know your gear, you got to know the bearings, you got to know what those sizes are. And then the other thing is you got to look at these things and figure out where the stress concentrations are going to be on this thing. So right now, without the step shaft in this, this thing is going to be right here. I got a groove there. I got a groove there. And I got a stress concentration there on both sides. Okay.
So, assuming we end up picking a design with a keyway, for the
crap, yeah,
keyway,
there's
do
another
you
one.
want us to do key design? Do you want us to find the shear
Oh yeah,
stress
you want
across
to make
that
sure the
plane
key's
and
going to be
pick a
right too.
material?
So
Do you want us picking a material for it? Do you want us like choosing, something that's gonna fit within our design parameters?
Yeah, I mean the keys are going to have to. The material you choose for the key has got to be something that is workable. I mean, you don't want to choose a bismuth key and have it fail every time, but you don't want to choose, a 4140 would probably be stupid.
Yeah, because it's the same material that the gear is made
Right.
out of, so they'd break at the same time.
So yeah, I mean, and maybe what this comes down to is we come back up to you guys can't see that, wrong screen. Come back to this bit and just say, okay, screw it, we're going with design 2, and everything works. And literally with the shaft, with the little bit of space we got, I can't see stepping a shaft up in size to make this thing work. And literally, there is no lateral thrust on the gear itself, and there really the bearings we picked have no thrust capabilities whatsoever. So if that's going to fail, it's just going to fail.
And I guess my last major question would be with the bearings. So, we know that there's a certain amount of deflection that's allowed, and I would assume that that's something that the manufacturer knows what that is. Is that something we can find in that catalog that you had up? Or is that something we have
need
to calculate
So
somehow?
if you go back to this, it's a
Like, I know we're gonna have to find what the deflection is, but how do we find what the allowable deflection is?
well, let's go back at it this way. And lucky for you, I just tortured the sophomores. Except the problem I got here doesn't have that equation in it. Ha! Go figure. Hold on. Let me get the chart up here. Actually, it's funny too with the strength of materials exam today. The number of ways you can calculate a problem wrong when it's a given equation and you just got to plug the numbers in is fanatical. I mean, it's like, so first of all, the length of the thing needed to be X in inches and not feet. Walk by like, what are you doing? Well, I'm doing, no. Beam reactions, what did I do with these things? Oh, yeah, it's up in homework section. No, it's not in homework section. Where did I put this? Cool. And it's coming ever so slowly. There we go. Over here, please. All right. So for blow up, so the one you're looking for is, well, simply support a uniformly distributed load, but we need the one with a point and then uniformly distributed load. But I think literally play with this one. So it's this, and I'll pop back over to the other screen here in a second. But your deflection will be P times L cubed over 48 EI. And that's Y max. Okay, so basically it's coming off this table. Now, it would be nice, we should go back and put the weight of the shaft in there, but I got a feeling we're not going to see any real
Yeah.
deflection here anyway. So, and truthfully, in 6 inches, if this thing deflects a tenth of an inch, we probably got issues. So literally,
Okay.
it's
Well, so
this.
yeah,
So you want to come
how do
back
we
here
find?
and look at what it's got for bore and what their tolerances are on that. Do they specify?
Okay.
They don't specify. Yeah, they do give you a tolerance. So here's your tolerance. Bore tolerance is plus 0.001 and minus nothing. So when they say it's 1 inch and 3/16, you can pretty much take that right to its fraction and come up with it. So if we are, let's get back to the right screen here for a second. If we are right here and we know that it's 1.125 inches, okay, and that's our bore. We have it as 1.126 inches, and I bet the no, come on, lay that out there right. 1.25 inches, and those are going to be your tolerances you're going to play with. Okay.
Okay, perfect.
Now, if it's what 3/16 is, well, we picked 1 inch and 1/8, so it would be the 1.25. It'd go up to a little bit larger, but they're going to hold that as plus 0.001 and minus 0.000, and that's going to be your bore diameter. So literally, you're looking for, you can go, if the shaft was to bend like so, you can take it between here and what would be the center line. You can go up 0.0005 inches. Okay. And that's going to be your max deflection you can afford. All right. So it's splitting that tolerance in half. Make sense?
Yeah, that was perfect. That's what I was
Yeah.
kind of unsure about still. I think I get the rest from
Matt?
there.
Yeah, I mean, I think I'm all good. It's more or less just understanding what all like it all means in terms of everything else. I mean, I think I just got to start like plugging away at it, and if I get stuck, I can
Send me a copy
maybe
of what you've
message
been
you, or
working on and let me see it.
maybe my good friend James will help me.
Laura?
Seems to have his head
Laura,
wrapped
where are
around
you
this
at?
pretty well. So
I understand a lot more, but same as Matt, I think I'm just going to start plugging away at everything,
Okay.
and if I have
Well,
questions, I'll
just
reach out.
put it on comp paper and scan it and send it to me. I mean, we got time between now and Thursday to play with it. All right. Tim, where are you at?
all right.
Kind of as a repeating pattern. I think once I start going, I'll probably have questions, but
Tim?
so far so good. It's allergies, I
Sweet.
promise.
All right. Michael, where are you
Sonic
at?
screwdriver.
I'm at a similar state, Matt and Laura. I've got a decent wrap around what we're doing. I just need to actually sit down and do it, but finding the time to sit down and do it is proving to be difficult
Well, I don't know
in these
who's
last
got
few
other
days.
things for you to do, but they ought to take back seat priority. Who do I need to yell at?
Craig, Dr. Craig.
Yeah. Literally, I think, folks, we literally laid out in this thing pretty quickly a lot of the pieces and parts that you need to play with. And literally, when it comes to your design matrix, I don't care what you're doing. Why don't we just take that section right out, even though you know you should probably have one, and just work on design 2. Okay. We got the steps for the shaft. We got the other pieces, and you're going to calculate your shaft diameter and stuff based on that. Okay.
So in terms of like, I guess, project layout, we obviously are not going to have like the luxury of like doing this all. I mean, we could if we wanted to, but like putting it all online, I guess, with Excel and everything. So do you kind of just want us to pull out these sections of like long paragraphs and
As
like
far
just
as
put
I'm
them in
concerned right now,
as we go?
it's not modern
Stop
profession
doing
where I
it
want
stuff.
you to type it up like they did in their report. I start at the top of comp paper and just start doing it, and then put in a little blurb
Yeah,
that
okay, that's kind of
says
what I meant.
chose gear such and such, Boston Gear Catalog. So that we
Yeah, got it. Okay.
So like something like that, where you would put
Yep.
in like assume this gear, and we can just kind
You
of
got
keep
it.
working down like that. Cool.
Yeah,
So
All right.
I just want
that sounds good with me.
to. What is our like end goal for this? So we want to like choose all of our gears, have the best design, and then just have it all written out.
Well,
like
I
that?
want to
Or-
know that you've chosen a gear and bearings, and then ultimately the shaft will not fail. I mean, we're trying to design a shaft
Okay.
here, folks. I mean, let's get seriously. We're not designing a gear, we're picking one. Okay, we want to know it works on our shaft. Well, we don't know what our shaft is until we know what the hub diameter and the bore diameters are of the bearings and the gear. Once we know those two things, we got our limits of what the shaft can be, and we know it's 6 inches, and we want to make sure the shaft doesn't fail or deflect too much in 6 inches. I got news for you. The deflection on a 6-inch shaft that's 1 1/8 in diameter is going to be really small. I mean, it's not like you're going out 6 feet and having it deflect. I mean, there's a reason why we make things that small, because
right.
truthfully, you can get away with this stuff and no one cares. But having it make sure that deflection's small enough so that the bearing is in tolerance and that the meshing of the gears with the mating gear still work, that's what you're critical for. But really for this, I just wanted you to know how to choose parts and pieces, know that there's these steps in the way that you got to calculate things, and then prove to me that it doesn't fail based on the stress of the shaft being loaded this way. And if you get the maximum distortion
Okay.
energy theory fail, you go back to the beginning of the semester. All right. I mean, it shouldn't fail. I mean, we're picking a pretty decent piece of material, and you can choose almost anything. I bet you could choose 836 and still make a shaft out of this. So that's a cold rolled, not cold rolled, it's a hot rolled steel that it's got a yield strength of 36,000 pounds per square inch. Yeah, well, I wouldn't make a shaft out of that anyways. I'd make a shaft out of something a little bit better, 1095, 4140, 4120, something like that, okay? So that's kind of where that is. So all makes sense, parts and pieces wise? Cool. So literally,
Yeah.
I like what James is doing. Put it on comp paper and run right down through that. I mean, in a more formal world, you would actually take that and type it up and get it ready for presentation. I'm not in no presentation mode. All I'm after is I can prove to somebody that when you got done, you knew how to design a shaft and go shopping for the other parts.
Cool.
Okay? Cool.
All right.
Alrighty.
Sounds
I'll
good.
see you all later.
All right. James, I may message you on Teams tonight.